So what I want to present on today is thinking about how do we enhance online problems by taking an instructor-centered approach to doing experimentation. So we're trying to think of this question, well, how can we help instructors conduct randomized A/B experiments? Well, why would that be helpful? The key idea is we have an opportunity that instead of relying on our intuitions when we're teaching, we could actually collect data about alternative instructional approaches to see what students find helpful. Of course, there are many obstacles. Instructors have to invest a lot of time and effort to actually program experiments. And so we're going to present a system that's for A/B testing in online problems. If you think of an online problem like this one here, they're ubiquitous. You might use them in on-campus courses. You might give quizzes in MOOCs. So we want to make it easy for instructors to test different elaboration messages. For example, which explanations do students find helpful? What learning tips might be useful? And we choose this for a couple of reasons. One is that online problems are ubiquitous, and the other is that there's actually a lot of evidence that these messages can help, but it's not always clear which ones are useful. So there's been work on technology for experimentation. Tools like Optimizing Industry let people A/B test their websites to see what increases engagement, but these are hard to adapt to the educational setting because they require programming experience, and they also don't often integrate with instructors' courses, with the security and privacy concerns you might have. There are tools for platforms like edX and Assessments in education, but although they allow randomized experiments, there's still a lot of effort in actually getting the data from these experiments and then using it for improvement. We draw on work on how do you involve instructors in research. Like design-based research actually helps instructors work with researchers to create artifacts. Here we're having instructors create different conditions in experiments. And as I mentioned, elaboration messages and online problems, there's a lot of work that these can be helpful, but often it's not really clear which ones are until we actually test them out and collect data. So to give an overview, we're going to tackle these design goals for a more instructor-centered approach to experimentation. These are first, making it easier for instructors to run experiments, and second, actually helping instructors use data from experiments to enhance learning. We've therefore introduced dynamic problem. So this is an end-user tool that instructors can use in on-campus courses and MOOCs to actually test components of online problems. And we implement an algorithm in the system that will do dynamic experimentation, analyze data, and use it to help future people. We present insights from our deployment with 3 different instructors. So what are our goals for a more instructor-centered approach to experimentation? One key one is the instructors in our field observations from deploying experiments over 5 years and also semi-structured interviews, they often report that deploying experiments seems to require a lot of time. They've got to actually make modifications to a platform and hire programmers. So we'd like to provide an end-user plugin that helps do that for them. The second is that the instructors actually want data from experiments to be used. And this is why we implement an algorithm that will actually use reinforcement learning to automatically give the most effective conditions to future students. So here's an overview of the dynamic problem plugin. Basically, you can embed this tool into any learning management system, like Canvas or Blackboard, or any MOOC by the Learning Tools Interoperability Standard. So you stick it into the platform you're already using. So let me first show you the student view and then the instructor view. So for students, it's actually a lot like the normal quizzes they receive. They see a problem and they attempt it. Eventually they get told the correct answer, and then they would be given an elaboration message. For example, an explanation for how to solve the problem. This is where the randomization happens because the alternative messages they can be randomized to. We then ask them to rate, well, how helpful was this information for your learning on a scale from 0 to 10? So we use this subjective judgment for 2 reasons. The first is that it's actually a lot like what you use when you teach in person. If you explain a concept to a student, you're actually trying to read, was that helpful to them? And the data you're collecting is facial expression, or what they say. This is actually a quantitative analog where students are actually rating how helpful something was. And the second is that even though this is subjective, in our past work at Learning at Scale, we've actually found that when you choose messages that students find helpful, it does actually correlate with the messages that will actually help them learn. Well, what does the instructor see when they go to this page? They actually see not just a student preview, but also an interface where they can actually create alternative messages. So in one of these instructors' cases, they could see the message they had originally, which was feedback, correct. Since f is always negative, it's always decreasing, and it reaches its lowest point at the far right endpoint of the domain. but then they can actually add a new message. So they can actually author an alternative version of that. In this setting, what the instructor actually did was take the original message and add a learning tip on. If you want to review this kind of question further, look back at your notes about where we found where the function g was greatest and least, and also look at this relevant video. So they're now testing would adding this learning tip be something that students would find helpful. The instructor then actually gets a dashboard, so they see this data come up in real time. So they can contrast these two messages, one with the learning tip and one without, and they can actually see students' mean rating, as well as how many students rated it and what the standard deviation was. So we deployed the system with 3 instructors. These were instructors at Harvard who were teaching a course on public policy, on calculus, and on statistics. And here are the key insights we got. One is that all instructors actually were able to use the system to deploy an experiment. Something that might have taken hundreds of hours actually took on the order of 5 to 10. So instructors reported this actually lowered barriers for them. I'm not aware of any tools that do this sort of thing. Well, even if I found one, I wouldn't have the technical expertise to incorporate it into my course, where this directly plugs in through this learning tool's interoperability. Another interesting insight was that they found that just engaging in experimental design helped them reflect on pedagogy. I never really seriously considered testing multiple versions as we're now doing. So even if we don't get any significant data, that will have been a benefit in my mind. And finally, they felt that this was making research practical. So it's a valuable tool. It's putting in the hands of the teacher to understand how their students learn, not just in broad terms, but specifically in their course. So this deployment, this proof of concept, provides some evidence that this can actually get instructors to run experiments. But what about the second goal of having instructors use data in a practical way? So in using data for practical improvement, some of the instructor concerns are, well, experiments often advance researchers' goals. They learn something, they can publish a paper, but how is it helping their students who might be involved in experiments? In particular, instructors are concerned about the ethics of giving students conditions that we might have evidence are unhelpful. So our approach to this is actually to think about dynamic experimentation. So borrowing on past work from industry A/B testing and also reinforcement learning, we implement an algorithm that actually analyzes data from the experiment in real time and use that data to give higher rated messages to future students. So the way we frame this computational problem of dynamic experimentation is known in reinforcement learning as expiration, where you're testing out and randomizing to see what's effective. This is exploitation. How do we actually use the data we've collected to help people? So we model this as a multi-armed bandit problem, which is a subset of reinforcement learning. So a multi-armed bandit is essentially saying you have a set of actions. For example, elaboration message A, elaboration message B. What you want to do is choose these actions to optimize a reward. In this case, the reward would be rating from 0 to 10. So we want to optimize the ratings that students are giving to messages. So what we need is a policy. At a given point in time for student 1 or student 20, what message do we assign? And the algorithm we use here is called Thompson sampling. And you can think of it as randomized probability matching. So when you see that there's a 70% chance of assigning message A versus 30% of B, let's say after 20 students, what it's doing is it's computing what's the probability, based on the data that I have so far, that A is the highest rated message. If it's 70%, then we assign 70% of students to that message. If the probability is 30% for B, then it means that based on the sample so far, there's a 30% chance that B is the highest rated. So this naturally does expiration exploitation. As you get more evidence something's effective, you give it to more students. So here are the technical details. The model we used here is essentially, we model the prior probability of a message being rated helpful as following a beta distribution. And the priors here were 19 and 1, which is analogous to saying before we see any data, it's as if people gave a rating of 9 and a rating of 10. Then to update and do Bayesian inference, we're assuming the reward or the rating follows a binomial distribution with 10 samples, where the probability of success is drawn from that prior beta distribution. So the idea here is that if someone gives a rating of 8, it's like they gave 8 thumbs up and 2 thumbs down. Every time someone gives a rating, we update our estimates of the actual underlying true ratings of these messages. So intuitively, the way this dynamically weighted randomization works is that initially you have a 50-50 probability of assignment. That's how we always do experiments. But as you're collecting data, this property is being updated. It might go to 60-40, 70-30, and the limit, it would converge to 100% of people getting 1. The key idea here is the probability at any point in time that the next student will be assigned to a message is the probability of that message being highest rated in terms of the underlying population, what's actually happening. Here's an example from Instructor 2. So here the instructor wanted to compare whether they should give a quantitative explanation of how statistical power can be computed or an analogical explanation. And by the time this experiment was wrapping up, there was a 23% chance of assigning the quantitative explanation versus 77% for the analogical. And what's that reflecting is that there's evidence, or at least a trend, that the analogical explanation has a slightly higher rating than the quantitative. So it's not conclusive. And what the instructor appreciated is that they didn't have to keep checking this dashboard and doing statistical tests. It wasn't on them to figure out when to stop the experiment. This algorithm is kind of gracefully and naturally presenting something more frequently as we get more evidence that it's effective. But it's not stopping the experiment immediately. So the key observation from instructors was that they felt that having this algorithm in the dynamic prompt system meant that the experiment could directly help students. It improved the experience of many of the students by giving them answers that are more helpful. So the earlier ones can help improve the experience of the later students. So there was a clear pathway from if an experiment is effective, the data is automatically being used to improve a resource. Well, what are student perceptions of this? So after the third experiment, we actually sent an optional survey to students where we let them know that this is how randomization was occurring and got their input and what they thought about it. Overall, they weren't surprised by this approach and actually appreciated it. So they said, well, I assume companies are always A/B testing on me. But at least in this context, the data that I provide can actually help other people learn. So think about the limitations of this and how it sets the stage up for future work. I think we've shown that instructors can conduct experiments, but what's really key here is to help instructors conduct better experiments. Maybe 1 in every 10 experiments yields data that's going to lead to practical improvement. So we see this as really just the first step in seeing how do we lower the barriers. And now it's up to instructors and researchers to help figure out what good experiments they can run. And so this tool is available as a hosted tool. You could go into Canvas right now or Moodle and just plug it in, or you can modify the open source code. Another issue is to go beyond subjective student judgments as the outcome we want to optimize. And so the idea here is that what we found is that instructors can get off the ground quickly by getting students' judgments. But once they're interested, once they're hooked on experimentation, they then become very interested in actually figuring out how do we actually collect measures of learning and how do we incorporate them into the system. Now, we don't see this as actually meaning instructors should just run experiments on their own. We actually think that by lowering the barriers, this kind of tool could be a setting for instructors and researchers to collaborate on co-design of experiments. And finally, something I'm really excited about is how do we use experiments to discover how to personalize? So instead of discovering what's working well on average, we can use methods like contextual bandits to discover which messages might work for subgroups of people, like people with low versus high knowledge. And we actually have this Moodle web service where you can plug in algorithms from reinforcement learning to do this if you're running experiments. So just to summarize, I started with these design goals for instructor-centered experimentation. Let's lower the barriers and make sure data gets put into practice. And we presented this end-user tool that can plug into online courses, as well as on-campus learning management systems. We showed how you can use multi-arm bandits for dynamic experimentation and presented evidence that instructors see the value of this approach. And I think this is just the first step in a wide range of interesting future work for democratizing experimentation education. And so I'll just end with a reminder that PhD students can now apply to U of T computer science to education research and also advertising your postdoc. And again, there's the Learning and Families Subcommittee for CHI next year. Amy Ogan and I are subcommittee chairs, so please encourage people to apply to it. All right, thank you very much.